Okay, so what we're going to talk about today is in what we're going to talk about today is compounds. Specifically, we're going to talk about how to name these compounds. Let me pull up one adjustment here. Okay, so we're going to talk about what is different about bringing. Well, first of all, a compound is bringing together different elements, but there's more than one way to bring them together. For example, when you one thing to be clear about is that a compound is not a mixture. I mean, there's only 118 elements in the known universe. However, there's over 183 million different substances. They're arrived at by chemically bonding together atoms of different elements. Hey, the a compound is different than a mixture, though. It's not the same as just bringing together hydrogen and oxygen atoms and coexisting. I mean, hydrogen and oxygen are both gases. I can fill a balloon with both hydrogen and oxygen, and yet that hasn't formed a compound. On the other hand, if I break down the particles that make up hydrogen, hydrogen being diatomic, and I break down the particles that make up oxygen and I recombine them, I can create a new kind of particle, a molecule that is a mixture of both. And what's different about this is because I've changed the particles, I've changed the properties. Instead of two gases at room temperature, I formed something that's a liquid. That material that's now a liquid at room temperature has other properties unique to it. So understanding the nature of compounds is really going to come down to understanding the nature of these particles. Now, there are some terms we're going to use as we start talking about these particles. And you've seen this slide before, and I'll bring it up again. But just as a reminder, when we talk about these particles in the most generic sense, I'm just going to use the word particle. When I talk about atoms, I will be specific and say atom. And when I combine multiple atoms and fuse them together, I can form a molecule. If that molecule or that atom has a charge on it, instead it's an ion. When we're talking about these particles, it's important to realize that they have different characters to them. One is if a particle is made up of only a single atom, then we're talking about a monatomic particle. That's true whether I'm talking about an ion or just a loose atom. That's a monatomic particle. If I bring together two of them and fuse them together, then what I'm forming is a diatomic particle. A particle that is made up of two atoms, a molecule of carbon monoxide or a molecule of bromine, is got two atoms attached to each other. You can have more complex particles with 3 and 4 and 5. We will say diatomic or triatomic. We can even say polyatomic as they get bigger and bigger. Now, one of the terms that's going to come up a lot today is binary. Binary and diatomic often get confused with each other. Diatomic means two atoms. You know what binary means? Anyone know what a binary compound is as opposed to a diatomic compound? When I'm talking about binary, I'm not talking about the number of atoms in the particles anymore. I'm not talking about two atoms fused together. I'm talking about two flavors of atoms. Remember, the word element can mean two things: a bulk quantity of a substance made up of only one flavor of atom, or it can mean the flavor of the atom. And if I make something like carbon monoxide, which has a carbon atom and an oxygen atom fused together, that's two different flavors of atom, two different elements. Carbon monoxide is a binary compound. It's also diatomic, but in contrast, water, where I have one oxygen, two hydrogens attached to it, that's actually a triatomic, three atoms connected. But again, only two flavors of atom, oxygen and hydrogen. When you have something that is made up of only two flavors of atom, two elements, that's binary. That's going to be an important term as we go forward. We'll come back to this slide as we start using those terms a little bit more. All right. But this class is really about combining different elements to form new compounds. There's at least three ways to combine elements, to fuse, to bring atoms together to form compounds. The first way is metallic bonding. Metallic bonding, well, remember the defining property, the property that makes a metal, is that it does a lousy job of holding on to its electrons. If you bring metals together, they're going to bump into each other, like people with their arms full in the library or at a convention, or maybe at a concert. And if their arms are full and they're not good at holding on to those things, some things are going to fall off. Now, no metal wants to lose electrons, but it's kind of like the person at the library with an arm full of books. They're going to drop one by accident anyway. And when they drop that book, all the people around them are going to reach for the book to hand it back to the first guy. When that happens, all of the people get pulled together. Metallic bonding works the same way. You put a bunch of metal atoms together, a bunch of gold atoms together, they bump into each other, so they're going to lose some electrons. Then all the atoms pull together to grab that electron, and that causes the atoms to stick together. And this is what makes an iron nail solid or a gold coin solid, is all of these atoms losing an electron and then kind of all pulling together to grab it over and over and over again to form a solid material. This is why a gold coin is solid. This is why a copper penny is solid. It's also why a bronze statue, which is made of both tin and copper, sticks together. That's metallic bonding. We'll come back to metallic bonding in the future, but it's really a pretty straightforward process. In contrast, we have another kind of chemical bonding. It's very different than the first one, but it is another way in which atoms stick together. This is ionic bonding. Ionic bonding works by a different process. With ionic bonding, when you bring together two atoms, usually from opposite ends of the periodic table, say lithium from the left side of the periodic table and chlorine from the right, when you bring them together, well, the metals, again, they don't hold on to their electrons very well, but the nonmetals are aggressive at grabbing electrons. So when you bring chlorine next to lithium, chlorine will reach over and literally rip the electron clean off of lithium. As a result, now chlorine has one more electron than protons and lithium has one less. They become charged particles. Those charged particles then snap together. When you have both two charges next to each other, they snap together and form a bond. But this isn't what lithium chloride looks like. Yes, the plus and the minus stick together, and we will describe lithium chloride as a combination of those ions. But the reality is, when you bring lithium and chloride together, well, there's other lithium atoms around and other chloride atoms around, and lithium, for example, with its plus charge, is going to be attracted to a chlorine on the right, but also a chlorine on the left, and a chlorine above and a chlorine below. It's not directional. Plus and minus just kind of snap together, and they form these large grids, these arrays where you have alternating plus, minus, plus, minus, plus, minus. This is ionic bonding, and it's a little bit more involved than metallic bonding. There's more details to it, more things that we can explore. But ionic bonding is still on the simple side of what we can do here. When we want to take a look at different kinds of bonding, the next more complicated form of bonding is covalent bonding, and this is the winner. Covalent bonding lets us form very intricate molecules. Covalent bonding is what happens when two atoms get together and they both try and grab on each other's electrons. For example, if I have two chlorine atoms, two atoms from the right side of the periodic table, both of whom are aggressive at grabbing onto electrons. If I bring them together, each will reach out and try and take an electron from the other, and neither will let go, which will lock them into a discrete bond. And that discrete bond is how we make molecules. Ionic materials make these huge arrays of alternating plus and minus, plus and minus. There's no molecule in there. But covalent bonding is what produces these composite particles that we call molecules. All right, so this is the start of understanding these compounds, the bonding that brings us there. Now, how do we represent the compounds that we form? One way to represent them is with chemical formulas, and we'll get into more chemical formulas next week, but we'll start it off kind of simple. Chemical formulas are basically just a way of saying what particles are involved in that molecule. For something like water, for example, you have an oxygen atom covalently bonded to two hydrogen atoms. And we want to represent this structure in a way that we can manipulate it on a written page. So what we do is we say, well, we've got one oxygen atom and two hydrogen atoms. We use the symbol for the element to represent the particle. The symbol for O, the flavor of that atom, to describe the atom in the center, the oxygen. And the symbol for H to represent the hydrogen atoms. Now, it's cumbersome to write each of the individual atoms, so we'll collect them together. We can use a subscript to indicate that there are two hydrogen atoms instead of writing each one separately. This is why water can be represented as H2O. Three atoms that combine into a single particle, two of them hydrogen, H2, and one of them oxygen. This is, and when you write this, if I write this in chat or something like that, I'll just write H2O. If you write this on a written page, always put the atom count, that 2, as a subscript. It's going to be important to differentiate it from other numbers that are going to appear in the formula. Like if you look at that next molecule, SO4, there are four oxygens. There are four oxygens around that central atom. This is a polyatomic particle. But in addition to the 4, there's a 2. And we don't want to imply that there are 42 oxygen atoms. That 2 represents an extra set of electrons on the whole particle. It's the charge on that particle. We represent charges with superscripts to differentiate them from atom counts, which are subscripts. So in this case, there are 2 negative charges. So I'll write SO4, superscript 2 minus. And we can explore how these formulas describe different particles. Do you see the particle behind me, CH4? How many atoms do you think are in CH4? What do you think? Well, there's 4 hydrogen atoms and a carbon atom, so 5 atoms. That's polyatomic. That substance is also binary. There's 5 atoms, but there's 2 flavors of atoms, carbon and hydrogen in there. And these systems can get more complex, but in each case, we'll show the charge with a superscript and the atom count with a subscript. All right, now these formulas can be used for different purposes. The simplest use of the formula is to represent the relative number of atoms in a substance. Things like sodium chloride, which don't make molecules, still have the same relative number of sodium to chloride. One sodium, then a chloride, a sodium, then a chloride, the sodium, then a chloride. These huge crystals have a smallest whole number ratio of 1 to 1. So we can represent sodium chloride as Na, the symbol for sodium, and then Cl, the symbol for chlorine, combined. Molecules can also have an empirical formula. If I take a substance like, for example, hexane has got 6 carbon atoms and then 12 hydrogen atoms around it. Now, if I make a huge pile of these things, the ratio of carbon to hydrogen will always be 6 to 12. As I add more and more and more molecules, it's still 6 to 12. The smallest whole number ratio between 6 and 12 is 1 to 2. So the empirical formula for hexane is carbon 1, hydrogen 2. Butane, the molecule that's on the screen behind me there, butane has 4 carbon atoms and 10 hydrogen atoms. So its smallest whole number ratio, its empirical formula, is C2H5. Every compound has an empirical formula, but only molecular compounds, where you actually form discrete molecules, these larger compound particles, only molecular compounds have a molecular formula. And when I want to describe butane, I don't want to just say the ratio of carbon to hydrogen like I'm limited to do with sodium chloride. Instead, what I'll do is I will actually give you a blueprint of that. I'll say that in that molecule, there are 4 carbons and there are 10 hydrogens. That's not the smallest whole number multiple, but it is the explicit count of atoms in that molecule. That's the molecular formula for butane. There's also structural formulas, expanded and condensed, even skeletal structural formulas. We'll talk about those. There's also a formula unit. The formula unit is the smallest repeating unit in either an ionic or a molecular compound. It's going to be equal to the empirical formula. The formula unit for sodium chloride is 1 sodium and 1 chlorine. The formula unit for in butene is 2 carbons to 5 hydrogens. So these terms are going to be important as we start trying to understand, and we'll use them to label and to describe and to work with the compounds. Formulas are important.